Okay, so here is question number 1. Now, question number 1 says the particle diagram shows the change of state for water. Okay, so changes of state is a key phrase there. And on the side here, we've got the particle diagram. So I think most people recognized the particle diagram for solid and liquid and water. The question says, state what is happening at points A to E in the diagram. Now, many people had the sense to recognize what was happening, and for example, for change of state E, wrote solid is changing to liquid. However, this question isn't really about describing it like that, it's describing it with the appropriate words. Now, for many people, I gave them the benefit of the doubt, but the correct answers are as follows. So change of state A here is from a liquid to a gas. So that would be evaporating, or you could have boiling. Now change of state B, this one here, is from a liquid to a solid, and that one would be freezing, or possibly solidifying. Change of state C, which was the most difficult one, was from a solid to a gas, and we would call that subliming or sublimation. Then change of state D is from a gas here to a liquid, and we could call that condensing or condensation. And then E is the change of state from a solid to a liquid, and that is melting. Now, there wasn't a mark for each one. The marks were actually, as you see here, 3 marks. So if you got them all right, you got 3 marks. If you got 3 of them right, you got 2 marks, and 2 of them right, you got 1 mark. Okay. It says here, state the name for the type of change occurring when a substance transforms from one state of matter to another. Okay, so we were looking for what that type of change of state is called. Okay, and this is a physical change. It's called a physical change because it can be reversed, it can go back. All these changes here are all reversible. You can melt and then you can solidify. Okay, you can boil, you can then condense. So physical changes are reversible. Okay, this next question. Solids, liquids and gases have different properties. Some of these are described in the table below. Tick either 1 or 2 boxes in each row to show whether solid, liquid or gas matches the description in that row. Okay, so it flows easily through a pipe or a tube. So that could be used to describe a liquid and a gas. It can be compressed into a much smaller volume. Well, that only applies to a gas. It can take the shape of the bottom of a container. That would be a liquid. It has a fixed shape and is rigid. Well, that would be a solid. It can fill the whole space inside a container. That would be a gas. Okay. And for these, it was 1 mark for each row. Okay, this next question is all about heating and cooling curves. Okay, this particular one is a heating curve because the temperature is going up. So it says Kerry wants to know the boiling point of a liquid. She heats the liquid and measures the temperature every minute using a thermometer. Kerry plots her results on the graph below. Okay, so we can see that every minute from the 0 minutes, she's plotted her points and then she's joined them with a line of best fit. Notice here we've got 2 slightly anomalous results, or one of them is anomalous. And consequently, she hasn't gone through the points themselves, she's gone between the points. Tick 1 box to describe what's happening at point A on the graph. Okay, so at point A, we can see that the temperature is rising. Okay, so from your work we did on this topic, you should know that that tells us that a substance is heating up. It's not boiling, it's not melting, it's heating up. And we know from the introduction here that she's heating a liquid. Okay, so the correct answer is the temperature of the substance is increasing. The temperature of the substance is increasing. There is no boiling going on, simply temperature increasing. And then use the graph to give the boiling point of the liquid. Now, a lot of you seem to make a bit of a meal of this, but I gave some people the benefit of the doubt because they were very close. But if you put your ruler on the horizontal section there, which should be recognizable, and extend it across, it points to exactly 100 degrees Celsius. Okay, so use the graph to give the boiling temperature of the liquid. It's 100 degrees Celsius. Now, it doesn't ask you for this, but if it's 100 degrees Celsius, it has to be water, which is the substance that you measured in your experiment. Okay, number 3. This question is all about diffusion, which we talked about in a lesson just prior to the test. When people spray deodorants and perfumes into the air, the smell travels from one side of the room to the other. This process is called diffusion and is shown in the particle diagrams below. So in these diagrams, we can see at the start of the process, the deodorant particles are all closely packed together near the deodorant can. As time passes, these particles spread out, they're getting bumped around by the particles around them, until eventually they're spread out throughout most of the room. Okay, if you could, the next diagram, we would see them all through the room. And this process of diffusion is where the particles of the air, in this case, bump into the particles of deodorant and randomly spread them out across the room. Okay, so use the words in the box to complete the sentence that describe diffusion. Each word may be used once, more than once, or not at all. Now, during the test, I was asked a number of times, could we use the words once, more than once, or not at all? But it's written there for you. So you must make sure that you write the answers. Read the question carefully so that you get the right answer. Okay, so diffusion occurs when a fluid substance, now a fluid, just in case you didn't know, is a liquid or a gas. Okay, because liquids and gases have got many similarities, so we use the word fluid to describe them together. Okay, so diffusion occurs when a fluid substance is at a higher concentration. So if we go back to the diagram, the concentration of the deodorant, which is the fluid in this case, is very high over here, and it's very low over here. There's none there, so that's high concentration. This is low concentration. Okay, so it's at a higher concentration in one area and a lower concentration in another area. The difference in concentration is called the concentration gradient. So gradient, we tend to think of as being like a hill. Okay, so if you think of a gradient of a hill, then at this end here we've got a high concentration, and at this end here we've got a low concentration. Okay, so the high concentration will spread into the low concentration, so eventually we'd end up with a situation where the concentration throughout the fluid was all the same. Okay, that's what diffusion does. So when something is transferred to a substance by heating, okay, so heating is a bit of a clue, right? So when you heat something, you're adding energy. The kinetic energy of the particles, so if you're adding energy, the kinetic energy increases. Each particle gets more energy, so its movement increases. That's what kinetic means. It means movement. The more energy the particles have, the faster they move around. Okay, so For more energy, they move faster. This increases the rate of diffusion. So if particles are moving fast, then they diffuse through the other fluid more quickly. So these particles have got a lot of kinetic energy, moving quickly, moving around, spreading out until eventually they spread out throughout the entire fluid. And the final sentence, a higher concentration gradient will also cause particles to diffuse more quickly from the higher concentration to the lower concentration until they reach equilibrium. Now, equilibrium comes from the word equal, which we know that what that means. It means everything is the same. So equilibrium is where all the particles are spread out evenly throughout the main fluid. So the deodorant particles will be spread out equally throughout the main fluid. Okay. Number 3, or nearly number 3. So you're asked here to state 2 factors that would increase the rate of diffusion of deodorant particles from one area to another. Okay, now in the question previously, you're told that when energy is transferred to a substance by heating, the energy of the kinetic particles increases. The more energy the particles have, the faster they move around. This increases the rate of diffusion. So if you weren't sure, you were actually told one of the answers there, really. Okay, so you could increase the temperature. If you warm up the mixture, then we'll see an increased rate of diffusion. Just prior to the test, we watched a video where some blue dye was put into some 3 different liquids of different temperatures, and we saw that the hot one diffused most quickly. Okay, you could increase the concentration at one end of the gradient. So if you sprayed lots of deodorant in the example on the other part of the question, then that would increase the concentration gradient, and the deodorant would diffuse far more quickly. Okay, so that would be the 2 main answers to increase the speed of diffusion. Okay, this next question, I think some people weren't quite sure about manipulating negative numbers. Okay, you did recognise there were negative numbers, but perhaps you didn't fully understand which way around to work with them. So the table below contains data about a group of substances called the noble gases. Now, this is an example of a question where you may not have heard of the noble gases, but it doesn't matter because the information that you need to answer the questions is given in the question. So we're told that argon melts at -190 and boils at -186. Helium melts at -272 and it boils at -268. So basically, these low boiling points means that all these materials are gases. Okay, they're gases at room temperature, which is 20 degrees Celsius or thereabouts. So use the information in the table to answer the following questions. State the name of the substance with the highest boiling point. So the highest boiling point is going to be the one nearest to 0. Okay, the one nearest to 0. And if we look here, krypton has got a boiling point of -152, which is nearer to 0 than any of the others. Okay, so the correct answer was krypton. But then here, a lot of people misanswered this because they didn't put it in increase in melting point. They put it in order of decrease in melting point. Okay, so again, it's probably a maths issue rather than a chemistry or science issue. So the one with the lowest melting point is, let's look at the melting points, is helium, -272. Okay, so that's a lot lower than any of the others. So helium would be the first one. And then the next one would be a neon. Okay, because neon is 249. Then we've got argon. at minus 190, and then we've got krypton at minus 157. Okay, now a few people wrote the numbers down. But it says here, give the names. In fact, all these questions are asking for the name of a substance. And then the final question, give the name of the substance that has the greatest difference between melting and boiling point. Okay, so if we have a look at these, so this one has got a difference of 4 degrees. This one's got a difference of 4 as well. This one has got a difference of 5, and this one's got a difference of 4. So the correct answer is krypton, as it's got a difference of 5 degrees Celsius. Okay. Okay, number 5 is another example of a heating curve. So it's quite similar. So this part of this curve here is the same as this part of the curve here. Okay, this bit here, right? So a test tube of crushed ice is taken out of a freezer and left in a warm room. The graph shows how the temperature in the test tube changes. So if we look carefully at the graph, 0 is here. So we'd normally expect the horizontal axis to be drawn across there. However, we've got a minus 10 on this graph, so that's why the horizontal axis isn't drawn there, it's drawn down here. And then obviously we've got the time measured in minutes. Okay, so this question is about recognizing what these graphs tell us. So this is ice, okay, from a freezer, and it's left in a warm room. Okay, so at minus 10 degrees Celsius, you'd expect the ice to be solid ice. Okay, whereas when it reaches 0, now 0 you might remember is the melting point of ice. Okay, then a change of state would happen here, and of course when ice changes into water, then we call that process melting. Okay, so stage B, we could say that the ice is melting, that's the key word, into water. Okay, so that's the answer that we're looking for there, melting. So we move on to the next question. Explain why the temperature of the water stops rising at 25 degrees Celsius. Okay, so if we look at the graph, after it's melted, the temperature starts to rise, and then it eases off, and if we carried this line on, we'd probably notice that it just carried on the same like that. Okay, now this is a little bit of a difficult question, okay, but you just need to read the introduction to find the answer. A test tube of crushed ice is taken out of a freezer and left in a warm room. Okay, now a warm room, normally we expect room temperature to be 20 degrees Celsius, but a warm room might be as high as 25 degrees Celsius. Okay, so basically the water here has reached the temperature of the room. It can't go any higher because it's not being heated with a Bunsen burner. Okay, so there's no mention of Bunsen burner here, so it's reached room temperature. All right, so the water has reached room temperature. Okay, which is 25 degrees Celsius. Now then, this next question did confuse lots of people. I did try and give you a little bit of guidance during the test, but I don't think that was taken up very much. So 4 descriptions, A, B, C, and D, of the ways that particles could move are given below. Okay, so these 4 descriptions here are the ways in which particles could move. So way A, particles move in the same direction at the same speed. Okay, now you probably don't recognize that description because it doesn't make a great deal of sense. Particles vibrate around a fixed point. Now that does describe quite well particles of solid. Particles are far apart, colliding occasionally. Well, that describes the particles of a gas. And then particles move past each other and are close together. Well, that we could use to describe the particles of a liquid. Okay. Now the confusion came because we're using the same letters here as we're using in the question. Okay, but there is the word stage just to make it clear what we're talking about. So how do the particles move in stage A. Okay, so if we go back to our diagram, stage A is where the ice is still a solid. Okay, so we should recognize this from our cooling curve, or sorry, our heating curve rather, that this stage here is when ice is a solid, because we know this to be ice, and it's -10 to 0. Okay, so which of these statements best describes the particles in a solid? Okay, and that would be statement B. Okay, but lots of people didn't fully understand what they had to write there. But B describes particles in a solid. And then it says, how do the particles move in stage C? Okay, well, stage C is where the water, because the melting's finished at this point, so the water is simply warming up, and water is a liquid. So we're looking for a description of the way in which particles move in a liquid, and that would be statement D. Okay, so those are the two correct answers for that one. Okay, moving on. Now, ice from a freezer is put in a glass of water at room temperature. The ice floats on the water. Now, we spoke about this phenomenon. We mentioned things like icebergs and the fact that pond life in the winter can survive because the ice floats on top of the water, protecting them from beneath. And that's because ice is less dense or less heavy than water, which is unusual. We normally expect solids to be denser and heavier than the liquid that they come from. Okay, now what does this observation show about the density of the ice compared to that of water? Okay, so we've just mentioned that water is denser than ice. That's not true. Sorry, that is true. Water is denser than ice. I was going to make more waters than my ice, the wrong way around. Okay, so water is denser than ice. Okay, ice and water have the same density. Well, that's not true. Water is less dense than ice. If that were the case, the ice would sink to the bottom. And ice has a higher density than water. Again, that would mean that the ice would sink to the bottom of the water. So it's in fact that first box there. Now, part 2 says that the fact that ice floats in water tells us something about the distance between the particles. Tick the box next to the correct statement about the particles. So if we have a quick reminder ourselves of particle diagrams, if you have particles which are tightly packed together, then you would expect that substance to be quite heavy. Okay, so when all the particles are tightly packed together, then that would be quite heavy compared to the same material where the particles are slightly further apart. And that would be lighter. So in the case of this material, the particles in water, which is more dense than ice, are tightly packed together, and the particles in ice, which is less dense than water, are slightly further apart. Okay, so the particles in ice are further apart than in water. Okay, that is the correct answer. Again, the first one. Okay, so they spread out, and therefore ice is less dense because the particles are spread out for the same number of particles. It's the greater volume for the same mass, basically. Okay, number 6. The table below contains data about a group of substances called the halogens. And again, this is an example of a question that you may never have heard of the halogens, but as long as you read the question carefully and interpret the data, then you should be able to get the marks. So, first question says, complete the table, and a lot of people miss this, to give the physical state, solid, liquid, or gas, for each halogen at room temperature. Okay, so in this box here, we need to write solid, liquid, or gas. Now, of course, you could just guess, but there's a much better way of doing that, is to look at these numbers here. So bromine melts at -7. What that means is it's at -7, it changes from a solid into a liquid. Okay, if we carried on going up the temperature scale until we get to 25, then 25 is not as high as 59. Okay, so 25, it means that it is still a liquid. If you carried on heating the bromine until it got to 59, that's when it would boil. That's when it would turn into a gas. But between -7 and 59, it's a liquid. And 25 is between -7 and 59. So bromine is a liquid. We do the same thing here with the chlorine, so we're thinking of 25 degrees Celsius plus 25. Chlorine boils at minus 101, sorry, it melts at minus 101 rather, and it boils at minus 34. And that means at minus 34 it's changed from a liquid to a gas. All the way up to 25, it's still a gas. Fluorine melts at minus 220, boils at minus 188. Okay, so it's definitely still a gas at 25 degrees Celsius, which is much hotter. Iodine, though, melts at 114. Now, 114 is higher than 25. So that means at 25, it's still a solid because it won't melt until 114. So it's a solid at 25 degrees Celsius. Okay, the next part says bromine can be solid, liquid, or gas depending on the temperature. In which physical state will the particles of bromine have the most energy? Okay, so if we go all the way back to the beginning of our paper here, solid, liquid, gas, these particles here are moving around all over the place. And from that, we can understand that they've got the most energy. Okay, so in which physical state will the particles have the most energy? That would be as a gas. Is bromine a solid, a liquid, or a gas when the arrangement of particles is close together but randomly arranged? Okay, so again, if we go back to our diagram, these particles here could be described as being close together but randomly arranged. That means we're describing a liquid there. Okay, the next one, close together in a regular pattern. Again, if we refer back to our diagram, here we have them close together in a regular pattern, and this is a solid. And then you can probably work out the final one, randomly arranged and far apart, is a gas. Okay, the final question now. Generally, this was not well answered. Many people didn't answer it at all. Okay, but you do need to get into the habit of answering these open questions because they're quite important as you move up through the school. So the Artemis 1 space launch system is a rocket which is used to take humans and equipment to the moon. Okay, the image below shows the Artemis 1 rocket just before takeoff. And we've got the fuel tanks labeled in the diagram, and it says the rocket has 2 fuel tanks containing liquid hydrogen and liquid oxygen. Now you might be familiar with certainly oxygen as being a gas. Okay, so they have to compress it down and they have to cool it, turn it into a liquid. Sorry. Explain why hydrogen and oxygen are transported as liquids rather than as gases. Okay, so if we look at our diagram from the front here, this is the gas where there's lots of space between the particles. This is the liquid where they're squashed together. So basically, if you transport your if you transport your hydrogen and oxygen as a liquid, you can squash more hydrogen and oxygen into the same space as you would do with a gas. Okay, so we could say that liquids have a higher density. Going back to the previous question about density, it means that there's more particles squashed together. So density, a higher density than gases. We can say that liquids take up less space or lower volume. So for the same mass of hydrogen, it takes up less space as a liquid than it does as a gas, and therefore more fuel can be carried. And if more fuel can be carried, then the rocket can either go further or go faster. Okay, so the rocket can travel further or faster, depending on what's needed to get it to the moon. Okay, so it will mean that the Artemis is more likely to get to the moon and get back again, obviously, which would be ideal. Okay, so that's all the questions there. So just make sure that you've gone through them all, corrected them all. If you need to rewind the video rather, you can do that. You can pause it, but make sure you correct your paper so that you know the answers should you be asked similar questions in the future.